Okay. So
how do they clean it?
actually, we have a.
Not these. These don't work. These don't work.
I think
we'll see.
How do they do it? Somebody's done it every day.
Actually, I think they used other things.
I know. So where is it? Because I would have
maybe weight cloth.
So I can have some. I will clean it. I don't mind cleaning it.
No, I will ask.
They will do it.
They will do it. I will ask.
But I want to start. So.
I will ask how they do.
सभा क्या बोले? हाँ, तो आपको क्या करना है कि उनको रजिस्टर का साइन ले जाना है, अमित का साइन ले जाना है। ओके। तो जो रजिस्टर की साइन के लिए डायरेक्टली चला जाऊंगा। हाँ, मैं संदीप वाली बता दूँगा। ठीक है। क्या नाम है डायरेक्टर रजिस्टर का कौन? संजय कुमार। तुमको जाने का टाइम बताऊँगा। So start.
Yeah, I'm ready.
Okay, ready? Hi, good morning.
No microphone today.
Okay, welcome back to the today is the fourth day, right?
Sir, they are using calling actually.
Okay.
वो ज़्यादा देर तक रह जाता है।
वो ज़रूरी problem है।
Is there a possibility they can leave a cloth like that? No. No.
Okay. So there is small change that tomorrow, rather than the afternoon, we have the feedback etc. Right? I'll complete it the 4 sessions. So after lunch, it's yours. Okay.
And this afternoon, we will restart at 2:30, not at 3 p.m.
No, I forgot. So yeah, I forgot. Thank you. So we start at 2:30 because he's having some task on 4:30. Right. Oh, then we have to tell the fellow that the tea should come at 3:30.
That's why I told you. Yeah.
Okay. You have the number?
No, sir, I don't have.
तो मैं बता देता
कितने बजे तक? अच्छा ठीक है.
4 बजे 3:30 बजे. Okay then.
Okay.
Thank you. I'll come back.
Thank you.
Yeah, sure.
Okay. Good morning. So today I'm going to talk about something that's really important, I think, and I was talking yesterday to Narendra about this. So today I'm going to talk about trustworthy synthetic data development and analysis. So actually, synthetic data is not a new thing, right? It's been around for a long, long time, but it has recently been formalized much more. And it got formalized because in the UK, the Royal Society, have you heard of the Royal Society? The Royal Society is a very famous learned body in the UK. Famous people that were part of the Royal Society are Isaac Newton, Charles Babbage, Stephen Hawking recently. In fact, my friend that I put on from Cambridge the other day, he's a fellow of the Royal Society. I work with the Royal Society a lot. I'm not a fellow. But the Royal Society did some work on privacy-enhancing technologies. And within that privacy-enhancing technologies, which we'll talk about wider in a moment, within that, they recognized the importance of synthetic data and so created a report. So I think the report you can find online. It was written by people at the Alan Turing Institute and commissioned by the Royal Society. But what it did is it gave a formalization. So it's actually just on archive, but we should publish it because it's about 2 or 3 years old. But it's got something like 240 citations. While it is, it really is a little bit for people who have some knowledge of mathematics or computer science, because it does have formal definitions in it, but it talks about how we should formally create synthetic data. And some of the work that I'm going to show you today comes directly out of that report. Okay? So the thing is, systems, and especially those with AI, require data, okay? So if you've ever seen anything about how much ChatGPT 3, 3.5, 4 use masses of data, okay? So data is really important. And why do we need synthetic data? Well, this is important for you to think, because where you can, sometimes you can use real data. Okay, so if you can use real data for any modeling or any system, do that. Yeah, but where you might need synthetic data, yeah, is where regulation comes around. So we've talked about GDPR a number of times. So if there are privacy issues, if it's private data and it's regulated, yeah, then you should use synthetic data. That's what we're doing with the Financial Conduct Authority in the UK. Okay, so I want you to think about these issues. Why? That's the first part of the synthetic data report. Why, what, and how. Yeah, or how, what, and why. But the why is important, okay? So, regulation, privacy issues. Another thing is, sometimes we talk about personal data and we say sensitive data. Now, I want you to be clear that sensitive data is not just personal data. It is sensitive if I am an organization and I have machines running in my factory. That might be sensitive information because I don't want competitors to know how often I run my machines. I don't want people to know what times I run my machines, yeah? So it's not always personal, it could be commercially sensitive data. So organizational sensitive data is another. Another one is when we don't have any data. What about when we're hypothesizing, yeah? Then we can't model on what I call seed data, right? So that is another element where you need synthetic data. And then, you know, if you don't have original data, you have to think carefully, is the data right? Yeah. And then finally, data quality. Yeah. So the quality of your data might not be sufficient. Yeah. Just because of some collection. So you enhance it synthetically. So an example would be, so here's a really simple example, right? If I am collecting, remember that digital ID project? If I am collecting fingerprints, yeah, it might be that there's gaps in the fingerprint, right? So I can't quite judge certain things. So what I do is I fill it in probabilistically. I think it probably looks like that, and then use that instead, okay? You can base it on other knowledge or things that you know to say the likelihood is here. Another example would be, you know, if you knew a data at a point there and you knew it at a point there, you might just do a linear, assume it's linear between the two. Yeah, use other knowledge. If you've got other data points, you could use a higher order interpolation. Yeah, or you could use something you know about physical elements of it. Yeah, so you may know that over this time it was constant, so you might decide to say, well, it was like that. Yeah, could look anywhere in between there, but in fact, it may not even be continuous, right? So you might have to assume. So if you've got poor data quality, you can synthesize. And that's what I've done by joining those two lines there. I've synthesized some data, right? These are not true points, all these. I just guessed them. Okay, so synthetic data is growing. It's getting a massive market. Yeah. So what we can see is the latest reports are 45.7% growth every single year between 2022 and 2028. So that's a market of more than $2 billion. That's huge. 45% is not a typical growth you would see in many economic areas, okay? That's not going to happen in banking. Even when I showed you stuff around security and stuff around IoT, yes, 45% is huge. And the reason is we've got more AI, so we need more data to power AI or to interpolate with AI, etc. So it's going to be massive. In fact, they're already saying that synthetic data is powering most of our AI. Most, it's more than half. Yeah. Forbes mentioned how it's transforming AI, and this article talks about it makes your AI even better, okay? And I mentioned yesterday about the fairness, right? We were creating synthetic faces to get more balance. Okay, so here's some things that I came up with for the paper. In fact, I've got a couple of papers in this area, and I've got quite a few in this area, but there is one that I did recently with the NHS, yeah? And what that was is we started with something called syntactically accurate data. So syntactically accurate data is data that you might have previously called sort of test data, yeah? Something that looks the right shape, yeah? So if you've got a name, you might put characters in it and not numbers, because names don't have numbers, right? If it's a date of birth, you would make sure there's no letters in it, okay? So you'd have something syntactically accurate so it matches. And then what you might do is say, okay, well, now I'm going to make sure it's ranged correctly, yeah? So I might make sure that the date of birth, yeah, is, it fits the number of days in a month. So you can't have the 63rd of January, or you can't have the 15th month, yeah? Or you can't have the year 7,000,003, okay? So you can do things like that. So if you start first with syntactical accuracy, then at least, you know, because anything else you're going to have, you want to be syntactically accurate, right? So that's the real baseline. And the paper that we've got with University College London Hospital really says, first of all, let's get the pipeline where all the structures are right. And then what we did, yeah, is we added in uniformly distributed data. Yeah, we put in some constraints first, the date of birth kind of thing, and then we said, let's just put in some data. So it was for a hospital. So we said, let's assume that somebody comes in at this time, they leave at that time, you know, and that was not based upon, you know, we weren't correlating the age of the person with the time. We weren't correlating whether they were male or female or who was it. We just started moving from a very random data set to looking at where are we happy to add in some accuracy, some fidelity to the data, okay? And what we might call fidelity, well, I'll talk about fidelity in a minute, is statistical accuracy, right? So we want to move from having just syntactically correct, the right syntax to the right statistics, yeah? But we've got to make sure that it's private and it needs to be efficient. And actually efficiency is non-trivial in creating this data. So what we really have is something like this. I want you to, so this is important to understand. So when you are deriving data, when you're deriving data from a given set, so if you're given a set of data, yeah, and you want to be protective of the data, you want to be private, yeah, you make a set that looks like it, yeah, and say, you know, this looks like it so you can do some inference. If the data that you generate does not look like the original data, then it may not be very good, right? It might not help you, yeah? If you're trying to identify fraudulent transactions, yeah, and you don't copy the kind of thing, you'll be, how can you possibly spot the pattern? You're training on the wrong thing, yeah? So it's important that we do that. So if you train a classifier for cats, yeah, and then you want to identify cars, how's it going to know? Because it's got no knowledge of the different categories, right? So you've got privacy, then you have utility, and finally fidelity. Yeah? So the fidelity is actually if you look here, fidelity is derived from a set of measures that directly compare the synthetic data with the real one. So that is actually statistical accuracy in a sense, right? It's how accurate is it to the real data, yeah? On the other hand, your utility is how useful it is, yeah? And I'm going to give you an example in a minute, and privacy we know. So those three things are really important to understand. Now then, I don't know if you've ever seen a picture before about what we used to do to test cars, right? So if you build a new car, before you're building it, you do some testing, right? One way that you can test how efficient a car is to test for aerodynamics, yeah? So I'll write it because you might not know this word, aerodynamics. Yeah, and aerodynamics is how the wind passes over it, right? Yeah. Now, how you would do that today is computer modeling. Yeah. How we used to do it is we would build a model of the car in clay. Yeah. So you would build a clay model of the car so it was the same shape. Yeah. And then what you would do, so it was geometrically the same. What you would do then is put it in a wind tunnel, and you'd see the airflows, okay? You could see where the eddies were and the vortices, etc. Also, if you wanted to build a new car, you would test it for crashing, yeah? And when you tested it for crashing, it would be a frame of a car. Because actually the panels are very lightweight, they don't do anything. It's all about the structure of the car, right? The metal frame of the car. And you put that car, and you put some seats in it, and you put some dummies in it, a crash test dummy, and you hit it into a wall and see how good it is, right? Now, what they both are is the frame model and the clay model are both synthetic versions of the car. They're representations, yeah? But they've got different roles. And this is what's important, because if you imagine using a wireframe car, a steel frame car, for aerodynamics. It would be pointless, right? If you used a clay model and drove it into a wall, it would be pointless to tell you about how good the car is. And this is my way of saying to you, what's important is if you have lots of data points in n-dimensional space, high-dimensional space, you need to choose the right points to represent the data. No point using all of the points, right? Because then you're maybe not being private, or why are you being synthetic? If you use all the points, just use them. It's like, but just like we don't use a real car, build it and then crash it, because we can't test and modify it, that's why we use synthetic, yeah? So what's really important is the utility is the usefulness for the task. And what's important about that is you want to be useful for the task, yeah? But you've got to make sure that you balance the privacy and make sure that the fidelity gives you the usefulness. It's not the same. You can have something that's not exact. For example, you can aggregate data a bit, right? And you can still say, so I'll give you an example, right? So this example is about how you can get good utility without necessarily lots of data. If you want to know the weather next Tuesday, then do you need to know the weather every minute for the last 6 months? No, you just need to know roughly what day. You won't get any real benefit, right? So sometimes you can get really good utility with a lack of fidelity because you don't need exactness, you don't need lots of data, okay? Especially if the task was, should I give Narendra a loan of some money? Yeah? It's just yes or no, right? So I don't need to be really exact, even close to the decision boundary. Yeah, that's all where it's going to matter. It might not matter too much. So we always have to think about that, okay? But one thing that's important is this interplay here. That's a really important interplay. What you're doing is you're balancing those two to give you the maximum utility. But utility, what is important is, here you've got to think in the back of your mind, if I define some synthetic data for a certain task, yeah, you may not be able to use it for another task because you haven't took the right properties. Yeah? So you've got something here, but these two need to balance. And the reason is this: if I have a set of data and it's private or it's sensitive commercially, if the fidelity is really high, it looks just like in every shape the original data, then actually you can infer a lot from the data, right? That's what happened with the kind of linkage attacks with the IMDb database and with the New York taxis. Yeah, even though you added you obfuscated some information. Okay. So what most of the things that are done now, we've got a couple of ways to make synthetic data. What we can do is we can make lots of what are called agents, yeah? And agent-based computing has been around for a long time, well over, you know, in the 1900s. And agent-based, you have to give some behaviors to an agent, yeah? And we've done this before in my group, and I did it with one of the co-authors here, Mirko. And what you do is you say, okay, well, I'm going to create this agent, and what it's going to do, and I'm going to create lots of them, but I say, okay, this agent is going to go out to the shop at 8 o'clock, then they'll stay here, and you'll do some probabilistic, you know, some Poisson distribution of, you know, he's going to stay at the shop for 20 minutes, yeah, some distribution, pick a random number from a distribution. After he does that, he goes home, he watches TV, and it's an agent, and you run lots of these agents, yeah? And then you get some data set that's got this population, this virtual population, and that's sort of like, that is how a game works, right? That is procedural modeling, yeah? You define some procedures. But now we've got these different kind of generative models, because the problem is, if you do that, how do you make sure, yeah, that there were only enough people in the cinema at a certain time that the cinema can hold, right? Because you've got your agent saying, oh, he now goes to the cinema, and you go, oh no, he can't go to the cinema. Yeah, well, do you have him check that he can go? Well, that's not very realistic. He's going to go to the cinema or he's not, right? So you've got all these different constraints and all of these things that interplay. So agent-based or procedural modeling is a bit difficult. So we do generative modeling now. And what we do is we build joint distributions of data variables by training on a real data set. So we get on a real data set where we can, yeah? Now what's interesting is the real data set, we can either do things with the real data, build something synthetically, yeah? And as we're going, say, does it sort of match? If it doesn't, do some adjustments. Does it match, yeah? Or what we can do is we can take some statistics and say, this new thing will match those. I'll make sure that it matches those, yeah? And that's how you do it, okay? So you sample from the learned distribution, and you preserve as many statistical properties of the real data as, well, not really possible, but as needed. The only thing about possible is it becomes costly as well. Okay, so there are two different types. You can have implicit models and explicit models, yeah? So the implicit model are quite well known. These are GANs. So if you've ever heard of style GAN, yeah? So that is a GAN is generative adversarial network. And what that essentially does is you create a network, yeah, some data, and because it's adversarial, you've got a creator and a discriminator. the discriminator says, hang on, you don't match my original data. So then the generator gets a feedback loop. It says, oh, why not? It says, but you don't fit because of this. Takes that feedback, creates another version, and then the discriminator goes, yeah, that still doesn't work, gives some feedback, goes around this loop until the discriminator says, yeah, that looks just like my data, okay? So you can do that, and it's implicit because you don't explicitly state what the marginals, it's just looking at some higher order thing. It says, you know, because it's a discriminator, it's not discriminating on specific points, it's looking at many different complex relationships in the two data sets. So there's a taxonomy of some of the work. This is directly from the report, so I might get an idea how old the report is, because there's 2021 there. Might be 4 years old, this report, yeah? But what you've got is your data types can typically be structured or unstructured. So I mentioned StyleGAN, which of course is an image. Here you've got many different types for video, for audio. One of my PhD students is working in this space at the minute. And the two for structured is typically tabular data or time series data. And actually, sometimes you can model time series as tabular.
So actually, I have it now down. How do we calculate statistical accuracy if we don't have real data? Suppose they don't have.
Very good question. Okay, so this is one thing that I talk about, which is there's a thing about access to data, okay? And you can have direct or indirect. Yeah? Direct access means somebody gives you a set of data. Yeah? Indirect means that you derive some data. So for example, in the UK, in the US, we have census data. I don't know if you have that here, but every period of time, you get collections and it says, what job do you do? What age are you? Are you male, female? What religion are you, etc. It gets all these things. It's asked the whole nation, typically every 10 years. Yeah, it takes a long time to compile. And they say, this is what it looks like. This goes back to Doomsday, but right, a long time ago, 11th century kind of things, when they did some census. But what you do is then you can say, oh, in the census, 46% of people were men. That is derived, it's indirect, right? Because you don't know it, but somebody calculated it somewhere. And in fact, it could be indirect of a sample or not, but it's indirect, yeah? Other times you can have direct where somebody gives it you. Another example of indirect is, and this is, there is a company called Mostly AI, yeah? And what they do is they do indirect access. So they will maybe ask you something about your data. So what I could do is, if I'm a service saying I'm going to create some synthetic data for you, I could say, right, so let's say I want to look at whether somebody should have a loan, right? And let's say we've got a table and it's got, right over here, because I've got the thing, gender, yeah? And we're just going to put male or female for this, yeah? Oh, right, it's not good there. Try this. Oh, good. Gender, male or female. Age, sorry, I'm sneezing. Age, occupation. Right, okay. Now, what I can do is I can say to the people, so they've got some data for all this. I could say, I would like to know what's the age distribution, yeah? And what they might say is, okay, you've got, in my data set, you've got male and female, yeah? And it's something like that, right? 54, 46. Yeah? Okay? So that gives you, so you ask them and they'll tell you, yeah? That's indirect because you've not got the data. Now the thing is, what you could do then is, okay, give me your age profile. Yeah? And I'm going to assume everyone's over 18 for this data set, right? It's credit card or something like that. So you've got 18 to 34. Yeah? And you have that many. Yeah? And then I'm going to say 34 up about, or 35 to 54. It's got that many. And then greater than that, I'm going to add it all up and it's that many. Okay, so just 3 classes of age. Okay. Now the thing is, if you were to try and do that, so you're going to try and get something that looks like the original data, you can copy what's called the one-way marginal. You can make sure that along here, when I add up all the males and females, yeah, the ratio is 46 to 54. When I look at the ages, I get a distribution like this, 25, 28, and 47, yeah? So I get that, so I can check that I get that, and I go, oh, so my data looks similar and I've ignored occupation. Okay, but let's say the occupation, yeah, let's say the occupation, there's 3 occupations. In fact, I'm going to say 2, yeah? Working, not working. Okay? 2 things, and let's say that is 80, 20. Okay? Now then, so I can do the one-way marginals, and that's where I'd start with. Let's try and make sure the one-way marginals, unless there is something that I know, because at the end of it, I've got something that says, did they get a loan, right? If I work out that the gender did not matter at all, it always does, but let's say it didn't, then I can say, okay, don't give me the gender, I don't care about that, I'll just do 50-50, yeah, without knowing it's 46-54. But let's say they're all important, right? So what you want to do is you've got to generate these things. So the first thing you do is the one-way marginals, and make sure that for your synthetic data here, yeah, so this is your synthetic data you're going to create. Make sure that they add up like that, yeah? The problem is, if in the real data, yeah, it was like that, what you will assume here, if you're arbitrary, yeah, is how do you know that your number, what's your age distribution of your males? Yeah, you've no control on it here, but maybe you balance it so it's 50-50. Both of them look like this. The number, that's the age distribution of the males and the females, yeah? But what if this is age, but then you looked at age in the real data, age of males, if that was the age of the males, yeah, then what you'd expect, because they're roughly even, right? You're going to have very little males, females, right? So imagine if that's what your real data is, but you've set both of your synthetic data to be here, because you've not captured it. You don't know that it looks like this. You've no idea because you didn't ask. If you have the real data, you can check it, but you have to say, I'm going to check it, okay? So there's a real thing about accessing real and synthetic data, but it's a good question about the direct access. So how do we decide what is the fidelity? So what you've got is lots of different fidelity metrics. You don't need to remember these, okay? These will be in your notes for you. but you can look at the total variational distance. You can look at the mean absolute error. So what is the average of the absolute error? So you don't say whether the synthetic data is higher or lower than the other, but what's the mean of all that? The max of the absolute error, L1 norms, L2, or Hellinger, or Jensen-Shannon divergence. You can use KL divergence as well, actually. So, and you've got to decide where you check it, because look at this. This is the thing. If you look, there are, in the adult data set on Kaggle, there are 14 different attributes, yeah? That gives you, there are 91 two-way marginals. So this is called a two-way marginal, a joint distribution. It's the distribution of male and average and male. And what you could do is you've got another distribution in my example here, which is, you could have a graph of real, age, male, employed, sorry, working, and you could have the different one, which is real, age, male, not working. Can you see there's loads of marginal, and look with this, when you get three-way, because there's 17 different attributes, you're at 680 relevant three-way marginals. Yeah? So we've done some fidelity testing, so you'll get these in the notes, but they're basically the adult data set here. There's different types of generation techniques. So copular GAN is well known, CT GAN as well, really well known, synthpop. So these are all, and what we've done is we've measured the fidelity, yeah? And what we did is looked at the ranking across different data sets and depth of marginals, yeah? Here's one thing, when you've got those 17 attributes, yeah? And in fraud, for fraudulent data, if you want to work out for a transaction, yeah, there is a format, ISO format. It's got hundreds of things in it, but actually now there's even more you can get, because you can get what's the operating system on this, what kind of phone is it, when was my last activity, you know, what angle am I holding the phone at? It's got so many sensors in there. You could look and say, is that important in fraud, especially with this authorized push payment fraud? But even when you get down to it, if you start with 50 attributes, yeah, you could see at 17 attributes, there were 683 way marginals. Where do you stop on the marginals, yeah? Because just like there was 3 there, yeah, what you might have something like that is something on, you might have a number that says previous payback. Did they pay back or not previously? Yeah? If they paid back, i.e. they'd had loads of loans before, you might say, we'll give them a loan, right? But you wouldn't want to do a 4-way marginal. It's just too costly to do some of those to look across all of that. So we typically do 1, 2, or 3. We do, most of the time, we'll do all of the one-way modules, or the big majority of one, not all. If it's many attributes, you know, but a good number of one-ways, then a selected number of 2, and no more than sort of a handful, 2 handfuls of 3-way marginals.
Actually, sir, I am asking, suppose we have taken n with marginals, right? So it is it correct to, it is increased statistical accuracy for?
Oh yeah, so look, the fidelity of 1 has got everything the same. Yeah, everything the same. So therefore, every marginal matches. Yeah, if it's an exact replica, every single marginal matches. Okay, and then there's ways that we can develop, look at the privacy risk. And there's a number of these, I think I've got a few. But one of these, for example, is distance to closest records. Yeah, which what you are doing is you're looking at training and holdout. Yeah, and saying how does the distance between the synthetic data and the training data match? Yeah. So what you want to do is you're going to train on this synthetic data. That's the whole point that you want to do, right? So you've got original data here, you've split it into some training data and your holdout data. You all know about holdout data, so you can test it, yeah? And what you want to make sure, yeah, is how does it look? Because if this synthetic data, yeah, the distance between the synthetic data and the holdout data is quite close, your problem is your synthetic data, it was trained on here, but it's giving, if you release that, you are giving some of that holdout data out, aren't you? Yeah? So you've got to make sure that the distance to closest record between these two, you don't want it to be, one thing that's important is, so these are all representing people. If you've got one person that's close, that's fine. Yeah, to have just one, because you need that, because otherwise, if you say none of those people looks like any of those, that's something an attacker can use for inference, right? Yeah, so you can have some, but what you want over the set, yeah, is that it doesn't go too far. So it's okay probabilistically to have one because it could just happen, but when you've got it over a number of records, then you've got a problem. So there are plenty of techniques that we can use. So a linkage attack, Latanya Sweeney came up with before. I think you mentioned membership inference attacks. Yeah. So a membership inference attack is you release this synthetic data, yeah, and you're trying to work out was somebody in that original training set. So actually, this has been done before, yeah, on membership inference attacks in general, yeah, because what you do is you get very good overfitted performance if something was in the original data set, okay? You can tell just how accurate it is, saying, well, it couldn't have done so well on this new thing that it never saw if it didn't see it in the training set. And a model inversion attack, can you determine the model that was used? So we use something called differential privacy, okay? And in fact, I've written there, it provides a strong guarantee. Well, it's a formal guarantee, yeah? It is a guarantee. It's a guarantee that you cannot tell data within it. Sorry, I asked yesterday, who's used differential privacy before? None of you, right? I remember, none. You have, you've used it. Okay, what kind of differential privacy did you?
As a defense mechanism or of attribute inference attack.
For attribute
inference attack.
Okay, okay, I'd like to see about that, how that works then. Let me see what my next slide is. Okay, yeah, okay. So this is used in the US Census data currently, yeah? It approximates complex data set, right? So what you do is you get, from the original data set, yeah, you can get the original marginal, yeah? And what it does is it says, well, hang on, let's not use the original marginal because does it matter if it's 4654 or could it be 4753? Does it matter that much? So it says, I'll put a bit of noise in. Yeah, so what you're doing is the more noise you add in, yeah, the more privacy you're adding, aren't you? Because you're saying, well, you can't tell so much. But the problem is the more noise you add in, the less useful it is. So you've got a balance here, right? So what it is, so here's one with a randomized mechanism M. Yeah, it gives epsilon delta privacy. If essentially what you're saying is the the statistics of the probability of somebody being in a set with or without an individual record, yeah, is bounded, essentially. So it's bounded, it's epsilon bounded, yeah, with some extra delta on top, some extra noise. So what it's really saying here, yeah, is I've got some statistic on a set, and whether somebody was in that set or not makes no difference to the statistic, because it's a noisy statistic. Yeah, so what that means is, and I'll tell you why we use it. So imagine in this room, yeah, I say, right, I need to find out the average age in this room, right? So what I do is I collect all of these, everybody's name and age, I get all the ages, I add it all up, yeah, and then I get an average age, yeah? Then somebody leaves the room, Narendra leaves the room. And I say, oh, let's do it again, let's do the test again. We do the test again, we get a new average, yeah? Now, the thing is, I can analytically, with absolute certainty, work out what Narendra's age is from those two numbers, yeah? Because I know one of them had him in and one didn't, right? Now, if I start to say, so that's really bad, this is where the idea came from. So what you do is you say, I'll add some noise. Now, if I add some noise to the age, and with or without you, now I've really got no idea what your age is because they're noisy, they're not exact, right? So what I could probably do is find out your age within a big range, right? The more noise I add, the range for your age is bigger because you've got less influence, okay? And that's what differential privacy is, okay? So the two types of approach where we use this differential privacy, yeah, and we can either, yeah, use synthesized low dimensional marginal distributions. So this was created by my colleague, Graham Kumar of Warwick, PrivBase, cited many thousands of times. In fact, the lead author on PrivBase, this is really interesting, has written in all his life so far 5 papers. That's all, because he went into industry. Every one of those 5 papers has got over 100 citations. It's a pretty interesting record. So really low index, really low I-10, but pretty good record, okay? So anyway, yeah, you choose the marginals, or you can have these GIAN-based methods as well. So the one that we tend to work a lot more on is the select, measure, generate. So what you do is you decide what are the important features, yeah? So that's the selection. Which are the marginals retain to some level in the new data set? So you select them. So first of all, you know, this selection can be by, you know, some empirical stuff, some thoughts, yeah? But what you do is you get those, and what you do is you query from the sensitive data a measure. You then add in a Gaussian function. So you add in noise from a Gaussian distribution, so it's randomized. Yeah, and the good thing about a Gaussian is that it's adding some noise, but it's you can take it out as well, right? So you get these noise marginals, and then you generate what? So this is private PGM. It's one of the most well-known select, generate, measure. Select, measure, generate, and you get your synthetic data. And this is applied to census data. And what can be done is looking at the minimum spanning trees to decide which are the marginal. So what you're doing with minimum spanning trees is saying where are the relationships that are important in the 17 different 17 different attributes. And then you've got occupation against sex value. So you've got one-way marginals, and you've got the minimum spanning tree. We've done the same thing on the financial fraud data set. Yeah, working out whether what works better, whether it's minimum spanning trees or not. So that's some of the key work we've done so far. Let me see what else I've got in. One second. Yeah, so what we've got is that's where we are with some of our synthetic data work, right? So what we've got is synthetic data is promising direction in many fields. You've got to balance, it's really hard. And it's hard because I want to tell you one thing about this differential privacy. If you're doing something private, if you release some statistics about synthetic data, yeah, you have used part of that, what's called epsilon budget, right? So epsilon, remember, is that bound, right? So I'm not sure, I don't have an iPhone with me today, but I think when Apple started with its using some differential privacy, and it typically uses it for predictive text, yeah? So what it does is it gets, you know, so let's say you've got certain characters or words or emojis is a good one, right? So let's say you've got a smiley emoji and you've got, and then you've got, I'm really bad at drawing. That's a thumb, yeah? So you've got these three things that you use a lot. What it does is, let's say that the frequency count that you used was 63, 24, and 13. What it does is it takes those original numbers and then it adds some noise to it, yeah? And the way that, so you now get something that comes out, and it might be 68, 21, and 11, okay? So you get that approach, but because across everybody's added some Gaussian noise, at the end of it, when I add it up, it should all balance out, right? And I'm going to go through one example for you of that. I'm going to show you quite easily, right? You see, nobody has coins anymore, do they? Okay. You got coins. It's got coins. How many of you got a coin on you? Or access to a coin? We might do, should we do a live test of differential privacy in the room? Okay, no, we need everybody to have a coin. Right. Everybody to have access to a coin, you can borrow it afterwards, right? I'm going to show you this, right? This is a real thing. My niece did it many years ago when I barely heard of differential privacy at this time when my niece was at school. She's now a doctor. So it's more than 10 years ago, but these ideas came out, right? I'm going to ask you to do something, right? I want to work out how many males and females in this room. It's not, in fact, okay, hang on. I've got to think about something else because we're really imbalanced on males and females in this room. So let's think about something a bit more balanced. Okay, I've got it. Let's do if you've got facial hair or not, right? So a mustache or a beard, okay? So we're going to try and work out, right? I'm going to do a test in a minute, but we're not going to do this. But this is where the privacy is, right? So first of all, number one, toss a coin. Yeah? So I want you to toss a coin in a minute, and your coins have heads or tails, do they? Yeah? Okay, so if it's a head, yeah, I want you to tell me if you're male or female. Tell me if you've got a facial hair or not. Yeah? If it's a tail, then toss a coin again. If it's heads, say yes, and if it's tails, say no. Do you get that? Right, really clear. So toss your coins and then write down whether it was heads or tails and pass on to the next person, right? Now I'm going to watch you, but pretend that I can't watch you because you're doing this all in private, okay? So all of you toss a coin. Yeah. So toss the first coin and just say if it's heads or tails. Write it down if it's heads or tails. Write down heads if it's heads, so tails if it's tails.
What's called?
Have you all done it? Did you all flip?
No, not yet.
Okay,
So we need to go one by one because we don't have.
that's all right. Okay, yeah. Write it down, write it down. Pass it on. Have you got a coin now?
Yeah.
Yeah.
Don't need to get, just leave it like.
Yeah, you don't need to tell me that he's got a coin for you. It can be any mechanism, it's a random thing, right? So long as it's random, yeah, that's the thing. But I know, what I do know is, on average, half of you will throw a head or half of you will throw a tail, right? Agree? So, has everyone thrown their coin? Yes? No? You've done a coin, you've got a heads or tails? Okay, yeah, I don't need to know what it is. You know what? Okay, well, let's. Could you get up and pass your coin to the lady just over there? You have it. Have you thrown it? Running. Yeah, just toss it and get a head or a tail. Write it down. You've written yours down? Written yours down? Yeah, you've written. Okay, well, let's find out anyway how the statistics work. How many people in this room? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I'll take part. Right. Is that a head or tail? What's that? I got a head. All right, how many people got heads? I got a tail, I'm going to say. How many people got heads? Oh my goodness, 1, 2, 3, 4, 5, 6. This cannot, there's excuses. Right, we're going to do one more. Wow, I've never seen so many. There's something called an unbiased coin. Are your coins unbiased?
No, biased.
Are they biased coins?
No, unbiased. I think the tossing is not properly. Maybe.
I'm going to toss a coin for you all. Right, this will be quicker, right. Right, you ready? You are heads. Oh my goodness. Tails. Oh, didn't toss that very well. Tails. Tails. Lots of heads. For you. Tails. Right, let's draw start at the back. Tails. Lots of tails now. Heads. Start at the back. Heads. Right. This might not work, you know, you shouldn't do these things like tails and yourself. Tails. What's the head? This is a head. I'm a head. Right. How many people got heads that time? That's it? No other heads? Who got a head? You got a head? You got a head? Head? 5 heads. Right. I'm going to run through you 5 again. That's a bit closer. 5 to 7. You are tails. Who else? Sorry, here. Heads. Tails. Heads. That's pretty even so far, so just me. Heads. Okay, so I'm just going to change this a little because of the way. I'm going to change this to tails, tell me the answer, and heads.
So actually, the number of trials tossing a coin more.
It's good. You need a lot more than 12 people, but we're going to sort it out and I'll prove why it works. Right. So the tail. So those that got a tail originally, I'm going to ask you to tell me the real answer, and those that got a head, yeah. If you've got a subsequent head, just say yes. Even if you have a beard or facial hair or not, doesn't matter. And say no, even if you have or not, it doesn't matter. Okay? So let's go through now. Facial hair or not? So, starting with you.
Yes.
Yes, you have facial hair. So that's one. Next.
Oh, it's a very good test.
You got tails originally, so you just tell the truth. Facial hair or not?
No.
Okay. Yes.
Yes.
Oh dear. At the back? So you got no?
Yeah. Yes.
What did you get?
I get head in the first.
You got heads in the first time. And what did you get the second time?
Yes.
Heads and a tail. Look, heads, then a tail. You say no. Even though you have, I can see it, right? But do you see now, even though he said no, it's worked. Right, at the back.
Head.
So what are you?
First time.
I just want facial hair or not. What was
Second time.
Second time what you get? Also head.
two heads?
Two heads.
Yeah, so you end up with facial hair. No.
Yes. Tail and yes.
Okay. Right, put your hands up if you've really got facial hair. The real answer. How many? I can see there's one. Really, forget the test now. Put your hand up if you have facial hair. Hi. So 1, 2, 3, 4, 5, 6. Magic, it's worked. Oh no, 7. You've got facial hair. You didn't put your hand up. 7. So it's 7-5, right? It's roughly even, isn't it? For this kind of sample size, it's pretty close, right? You can't get closer apart from being exact, right? And this is what happens. So this said 50-50, but the real answer is 7-5, okay? Now this is how it works, yeah? Because what happens is, and I'm sorry we're going over a little, yeah? Imagine there are the real thing, and you can replace it with X's, this, because it works, yeah? But imagine the number of males and females was, let's say, 60-40, yeah? How many of the 100 people are going to toss a head? How many of the 100 people will toss a head?
Is that?
No, everybody's got the 100 people, 60 of them are men, 40 of them are female. How many of them will flip a head and how many will flip a tail? Out of 100 people, how many would you expect to flip a head? You would imagine 50, right?
Yeah.
If it's unbiased, it should be about 50, right? But let's say it wasn't. Let's say it was, it's not exact, so 52%, 52% of the total rolled ahead. And then 48 with the tail on the first go. Yeah, agreed? Yeah, it's roughly okay. How many of the men will have rolled a head and how many will have rolled a tail? Well, there were 60 men, yeah? How many do you think rolled a head?
32.
Roughly, it could be anything like that, around 32 or something like that. So 32 rolled a head, yeah? And that means 28 rolled a tail, yeah? And for the females, yeah, let's do 21-19 or something. Yeah, so we're not being exact, but we're saying roughly, yeah? Now then, what happens is, you can do it overall or we'll do it each one, right? How many of the, so our rule is, if it's tail, you tell me the truth, yeah? And if it's a head, you toss a coin again, yeah? And say yes or no. So out of the 32, they're all gonna flip. How many are gonna throw a head and how many are gonna throw a tail? Should we just split it 16-16 this time? Yeah? So what you do is you get 16 heads and 16 tails, yeah? And then we do the same on this side, yeah? How many of the heads? Well, we're going to say 10 flip to head and 9 flip to tail. That all seems plausible to you? Yeah? That seems reasonable? Now then, what you can do is you can work out, you add up how many answers we get. We don't know who did this. We don't know anything. We just get, as a server, some answers. And the answers that we're going to get is we're going to get 28 men who told me, so the total males are 28 from here, yeah, because they tell me the truth. And we're going to get, of the 32, 16 are going to say they're men and 16 are going to say they're female, even though they're not, right? So you get plus 16, yeah? How many of these people are going to tell me that they're male? Well, none of the ones telling the truth, right? They don't tell me they're male. Of the heads, 10 of them said a head, so they're just going to say, yes, they're male. Yeah? And for the female, have I got this right? Let me see. Oh, I've got it wrong. What have I done? I've done something wrong here. Oh, hang on. No, I have to. Hang on. No, this is wrong. Hang on, just give me a second. I need to do it for you later because I need to use. Let me just see. Yeah, so I'm going to get these numbers. Because that's not enough. Oh no, hang on, no, it's not enough. Hang on. Let me see anyway. For the females, I'm going to get 16 from there, and I'm going to get 21 from there. So actually, my ratio is 46-54. Sorry?
It is same before we are assuming.
So basically, originally you have estimated as 50.
Yeah, let me have a look at it and just work through that. But that's the process. The key thing is when you do this mechanism, yeah, because you're taking away how many lied, yeah, you don't know this 60-40 originally, but you know half are telling the truth and half are lying, yeah. So you can actually, and you can actually do it with a biased coin as well, it'll still work, but you can actually take away the noise that you've added, yeah, and you will get something that looks similar to the original, yeah. How much noise you add changes how accurate it will be. So you don't need to say, you know, here it's half the people throw the coin again, yeah? But the interesting thing is, what's really important is when somebody says to me yes or no, I don't know if they're telling the truth or if they threw another coin and they're lying, yeah? So if you say to me, facial hair, or if you say to me, you know, last night I ate cauliflower curry or something like that, I don't know whether it's true or not, because you could be one of the people who's told the truth. And your phone can do that. You know, it doesn't use a randomized response like that. It uses a noisy response. But that's how differential privacy works, okay? Right, we are over time. So we're going to go a little bit shorter on the next session, okay? Okay, 15 minutes. Go.
No, I have a doubt. Like while we work with temporal data, like timestamp, how can we balance the importance between the attributes? Like in the case of transactional data, we have timestamp value, and that contributes a load in the case of detection of fraud.
Yeah.
So, like I was working in that area, and right now I'm also working. I found that the importance of temporal data is quite high compared to other attributes. So how can you get a balance between the attributes in that case?
But why do you need to create a balance? If it depends, if it's in the data that there's nothing else important.
But if I'm like performing a attack like evasion over the data, I need to create a synthetic data from there.
Yeah.
And in that case, I will have to tamper the timestamp value.
Yes.
In that case, I will have to maintain the uniformity in the data also.
Yes.
So sometimes what happens if I will change the timestamp with a small change, it's change alone. The results.
Yeah.
But I'm not able to maintain the balance between the original data and that fraudulent data that I created synthetically.
Because it's so weighted on the thing that you can only add noise. Yeah. So you're having to add lots of noise, which means it's not useful.
Yes.
Yeah. And that. So I have to think about how I'm going to look at your balance set. Maybe drop me an email.
Like there is a concept of imperceptibility, where we add the very small, we do this in very small change in the data,
Yeah.
but it creates a great impact over the results. So one thing, how can we justify that small change will very differentiate between that change that we did
So what year of your PhD are you in? Fifth?
Yes.
Okay, and so you're going to submit soon?
Actually, I need one more journal.
Okay, what journals have you got so far?
IIT Translation.